I'm blue. Pull the door to. You will sit in the back row, that's what happens. So we didn't quite finish lecture 4, so we'll carry on from there. And I was just about to start the 5 circuits that we'll be doing between now and Christmas. Although I realised the other day it's week 10 this week, so panic. Anyway, on with the peak detector. One of the commonest applications for diodes is the conversion of AC into a unidirectional current, which is the same as saying DC, but if I say DC, there's a half chance you'll think of something which is constant, which is not necessarily the case. It just has to never fall below 0. Or if it's always below 0, never rise above 0. So it's not necessarily a single value. And this conversion process occurs in signal detectors and power supplies. And it often depends on what the frequency is that's being converted. And I said there was a little map of the world, which is a bit too small to be useful really, but if you Google map of power supplies world or something, I'm sure you'll be able to steal the same picture I did, and it'll be bigger. Oh, come on. Now what's happening now is the poor old USB bus is going, I've got to pull the next picture down, and it can't. And very shortly, Addo will crash because they've got too many managers and not enough engineers. Try that again. I'll send them an email and say, you can have a packet of biscuits if you can make a decent PDF reader. See if one comes back. Right then, peak detector. So this is the first circuit. And we've got a diode, a capacitor and a resistor. So it's broadly of the same order as the circuits that we've been looking at so far. Nothing, it's not suddenly got very complicated. And the key elements are the source, which is V1, the diode, which is D1, and the capacitor, which is C1. And that's in parallel with a resistor R1, which is quite normal. The reason for that will become apparent as we proceed. And the circuit's got 2 distinct states. The diode is, I should really say it's got 3, but the diode's got the 3. It's either conducting, or it's on the point of conduction, or it's not conducting. But the circuit I want to discuss is only the 2. It's the bit where the diode is on and the bit where the diode is off. Because when the diode's on the point of conduction, not much is actually changing. Stuff will be happening in the circuit, but nothing major will be worth talking about. So the diode is conducting, which is the situation I've got above, and in that situation, a current flows from V1 through D1 into C1, and the voltage across C1 increases in proportion to the rate of change of charge that flowed through it. So, is everyone happy that the voltage between the anode and the cathode of D1 in this situation must be more than 0.7? If that's news, then perhaps go back and have a look at the last few lectures. And what about the resistor? Well, in this situation, the resistor will dissipate some power and some current will flow through it, and that current will be supplied by V1. Because, well, you could say the current will come out of C1, or the charge will leave C1, and it'll be a current that will flow through R1, and that charge will be replenished by V1. But it's much easier just to say, well, V1 supplies the charge. It's the same thing, more or less. So conducting is the top diagram, and if we were carrying on in the same format that we've been using so far, we'd say, since the diode is conducting, we'll replace it with a 0.7 volt source. And we'll drop that in place of the diode, and then we'll say, well, we could start turning off the sources now, but that would only give us the conduction state for a certain situation, and the trouble is the situations come and go now, because we have 1/2 cycle of AC which is above 0, and 1/2 cycle of AC which is below 0, and then the next half cycle will be above again. So instead of saying, oh, we'll switch off the sources, what we'll say is, we'll worry about the first half cycle, and then the second half cycle, and then the third half cycle is the same as the first. So we finished. And the deciding how the circuit works proceeds along those lines instead. So in this situation, what will C1 charge up to in terms of voltage? Biscuits involved.
-0.7.
Do you want a biscuit?
Yes.
There you go then. Some of my colleagues think I bribe you with biscuits, but it's not the case. In fact, it does a lot of cool stuff. It makes me wander around, which breaks up your attention span, and it encourages interaction. And I like that. So it's not bribery, honest. Although if you wish to feel bribed, and you're happy with that, that's cool. So it's V1 minus 0.7. Sorry? So what about the state when it's not conducting? Well, we can just remove the diode, same as usual. And in that case, a current must leave C1, assuming C1 has previously been charged. If the whole situation is in the state of quiescence, where there's nothing going on at all, C1 is uncharged, there will be no current in R1. But let's assume that we have just charged up C1 in the prior half cycle. We'll assume that the first half cycle was positive, and then the next half cycle was negative. So what I'm saying is the input signal will look like this, as opposed to that. Because in this region, nothing of interest will happen. So I'll start with the consideration of this one. Sorry, they should be the same height and so down. I'll start with the consideration of this one and then move on to that one. If you wanted to start with this one and then do that one, you'd have to do a third one as well, because this situation and that situation would be different. Because nothing interesting would happen in the first situation. Good, situations everywhere. So in the V1 is less than 0, C1 discharges through R1 and the diode switched off. And that's what it looks like if I said sketch a graph of the peak detector currents and voltages, that would be the model answer. So currents in red, input voltage in blue, and the voltage across the capacitor and the resistor, that's to say not the sum of those two because they're the one thing, they're in parallel, is the black line. And if you integrate the area under the, that bit there, and you integrate the area under that bit there, so you add up the areas, they will equal each other. Because it's a measure of the energy gained and lost in the capacitor. Well, it's a no, that's not true. Energy is not gained and lost. It's a measure of the energy which is put into the capacitor, or stored in, that's the word, stored. English has a word called stored. Stored in the capacitor, and then it's a measure of the energy which is taken out of the capacitor, and then in the next half cycle it will be stored again. And that's all I have to say about peak detectors. There was a review and a bear, but you can't have a bear because we're going to carry on. So this is today's official lecture. This just says what I did. So we just did it. So in lecture 5, more on peak detectors. So nice continuity there. And then I want to go on to the second of the 5 circuits, which is the voltage clamp. In fact, then I'll go on to a combination of the peak detector and the clamp, which are used to make a circuit which doubles its input voltage. And then we'll generalise that into a circuit which will make any required voltage from any given input voltage with a series of clamps and peak detectors. And then I've got a bit to say about the simulation of circuits using computers, and then that'll be it for 5. So, carrying on, there is a time constant, R1 and C1. That's to say, if you did C1 in farads times R1 in ohms, you get a number whose units is seconds. And if you're not keen on the idea of that, if you go on Wikipedia what farads is in base units and what ohms is in base units and do all the crossing out, you'll end up with kilograms over something times seconds over kilograms times something times seconds. Anyway, you'll end up with seconds. So there is a time constant, which is R times C. RL will give you a time constant as well. And if we make sure that R times C is much, much bigger than the period of the waveform that we put in, we will find that the capacitor is not really discharged very much by the resistor when we're in the negative half cycle. So, in this region here, the capacitor is charged up. In fact, we know where it's charged up because we can see that the point where the line meets, the red line means the blue line, and the green line means the blue line, and so on and so forth, is the point where conduction will begin. So on that point, the diode's got 0.7 volts across it and no current through it. And as soon as we pass that point, the current will flow. And it'll carry on flowing until we get to just about there. Now, it's difficult to see in this diagram, but the blue line is in fact 0.7 volts above all the others. So conduction will cease there. And then in this region here, the capacitor is discharging through the resistor and giving up its energy. And depending on what the period of this waveform is and what the size of R and C are, determines which of those lines you might end up following. And as long as you manage to make R1 times C1 much, much bigger than the period of the waveform, you'll end up in a situation where you've got something which is akin to the black line. Now, the important thing about the black line is not the fact that it's the highest of the lines that are there, it's that it's more or less straight, because all the others appear to be exponential. Well, alright, if they don't appear to be exponential, they're exponential. And the reason for that is the RC circuit's natural response, which you will hear about in 117 before too long, is an exponential function. In fact, if we go back into the lectures, I did a bit which I said was not examinable, and I did a little derivation and said, oh, you look it up in a table of differential equations and so on and so forth. That's the same exponential we're talking about here. So we've got to make sure if we want to, I mean the idea of this circuit is to make a DC voltage from an AC voltage. And under normal situations, especially for power supplies, we'd like the black line to be totally flat, if possible. You can't achieve that, but that's the ideal. So we'd usually make R1C1 quite large, if we can. Certainly as large as we can afford to. And afford is not necessarily a case of money, although it often is a case of money. It's also a case of space, and also perhaps a case that some capacitors will only work at 85 degrees C for a certain number of hours, and others will work at 105 degrees C. And if you've got a very small volume, which is already quite hot, and you fill it with a large capacitor, you might find the airflow around that component is something awful, and making it just a little bit bigger means you need a 105 degree component instead of an 85 degree component. And the trouble with the 105 degree component is they're much more expensive. So when I say it's important to worry about the size, not just the physical size, not just the money, the thermals and everything. Of course you don't have to worry about any of that yet, but if we're all real engineers, which you will be soon, you will have to worry about it. Unless you go off into finance or something. Right. So we try and make R1, C1 large in the case of a power supply, where we want a fixed value. And we'll discuss power supplies in the last lecture before Christmas, I would think. There is another situation, which is the case of a signal detector. So the black line is an AM radio signal. I usually give a biscuit for that. I'd ask, and somebody would say, and I'd give them a biscuit. Too late. So this is the, all right, what is the modulating signal? It's too easy. If the black line is AM, have a guess at what the modulating signal was. No radio fans.
Amplitude.
It's a word. It doesn't really answer the question, I'm afraid. Sorry. Thank you for taking part, though. You can have a biscuit for joining in if you want. You're all right? What, you want one?
Yeah.
Right, see, I told you you'll get hungry. It's a sine wave. And the reason why will become apparent in a bit. So we've got the black line is the waveform which is modulated, and we wish to get the information back which was modulated in the past. So at the transmitter there was some sine wave, and it was modulated with some modulation system onto another sine wave. And the mathematics that covers that will be in the second year course somewhere. And we ended up with the black line. And we're going to pass this into our peak detector in the hope of getting a sine wave back, which is more or less the same as the original. And we've decided to adjust the time constant of the circuit. So R and C multiplied together are changing based on the colour of all the other lines except the black line. So we've got the blue one, the green one, the yellow one, and the red one. Which would you prefer? The red one. You would prefer the red one. Why?
It's like the period seems pretty much the same. It's like sort of lines up even though it's up there.
Right answer. Nearly the right reason. Biscuit?
Please, yeah.
You have to stop asking questions because giving out biscuits takes up a lot of time. You hang on to them, we'll just pass them around. Right, ready? You sure? Let me just put this down so I don't blind anybody behind you. Oh, you got two. I'd keep the second one if I were you. Right. It is the red one, but the reason is not quite right. What has to happen is, if you were to look at the blue one, it's all right, well, I've got a very good follow in this region. So, okay, there's a bit of staircase on it, but the blue line is more or less the average of the peaks of the black line, which is what we want because it's a peak detector. On the other hand, as we're going down, the blue line completely misses. The capacitor cannot discharge quickly enough through the resistor. So either the capacitor's too big or the resistor's too big. Taking the green one, same problem. Not quite as bad. There's still some staircase in here, and there still misses here, so it's not very good. And the yellow one, you think, oh, the yellow one looks about right. Not really. It still just about misses. What you have to have is a bit of a staircase, even in the lowest point of the modulation. And once you've managed that, you know you're always following the modulated signal. And if you're not following the modulated signal, you can't recover it nearly as well as you ought to. The other thing to notice about this particular graph is that if you were to take the average of the black line, so if you did across the whole screen, or well, from at least from there to about there, if you said, I'll integrate it with 1 over t in front and get the average, it will be 0, because there's just as much stuff below the line as there is above the line. If you were to look at any of the others, you'll find they've got a DC component. This is the same, is what makes the peak detector do its job, and it's what makes it good for making a power supply as well. So there will be a unidirectional current. Yeah, voltage, current, same. Not the same, but one leads to the other. So all of the red and the green, the blue and the yellow all have a component which is DC, even though they are not constant. That's the important thing. Anybody got anything to say about the peak detector at all? Now is the time. Now is the time because we're about to discuss something which relies on the peak detector. And if you're not happy with it, it would be better to say so. Cool. None of you are really using the little yellow forms, so I haven't bothered, because I have to sit and tear them up. So if you are stuck and you prefer not to say so, you can always email me, if you wish. So, more or less the lecture, more or less, I'll edit that bit out, more or less the rest of this lecture is about the clamp circuit. And if you said there was a question on a paper, maybe a paper you'll sit in the near future, perhaps some sort of exam, and it said describe the clamp circuit, then for a mark or two, a circuit that fixes or clamps, in quotes, either the positive or negative extreme of a waveform to a defined voltage level. So this is handy in situations where you've got a signal that transmits as part of its information some DC component. So not only is there some modulated carrier, there is a modulated carrier, and there is some part of that modulated carrier resolves out to DC, and that DC means something. And the most obvious example of this is an analog TV system. I may have to come up with a new example because it's going out of fashion pretty quick, but it's in lots and lots of textbooks, so it's a good one to talk about. The average brightness of the picture is dealt with by a DC value. So we have to be able to know what the DC is going to be. And when we transmit the signal, the DC is changed because the modulated carrier has no DC component, and the peak detector recovers the signal and gives it some DC value. So our DC component's been buggered with, and we've got to get it back. So we can use a clamp circuit for this sort of thing. So it's secretly just a rearrangement of the same three components. We have the capacitor C1, the diode D1, and the resistor R1. The thing is that electronic components are heavily unionized, and I can only afford a few of them. And we have two situations. We've got the diode conducting, which I've got as the top situation, and it would be perfectly acceptable to replace D1 with a 0.7 volt source. I just haven't in the diagram. So you could make that 0.7 volt voltage source if you wished. That would be fine. This one's a bit more, no, it's not any more difficult. It seems to cause a lot more trouble. So, that's why I bought a pointer. This is the first half cycle. And what I've said is, for the first half cycle, from 0 to half a millisecond, so that's this distance here, the rising V1, so black line, is going up. So this end here is more positive than this end here. So this is bigger voltage. If you want to call this 0, that's fine. And the rising V1 will try and pass a current through C1 towards the output. And it will manage that because this is a signal, and C1 will have some impedance, and that impedance will be 1 over 2 pi FC. And a small current will flow through C1 and then through R1, and the diode will be reverse biased. Happy? Because this will be the bigger voltage, so this will be the bigger voltage, so cathode bigger than anode, voltage, diode is reverse biased. So the diode won't conduct, and the current that flows through R1 is the same current that flows through C1. So what we've really got is a high pass filter. It doesn't help to think about it like that, but it is the same set of components, laid out in the same way. And since the resistor, we're making the value of the resistor quite large, so the current that flows is not very significant. And that current does not charge up C1. So the same voltage appears here as appears here, is what we're saying. Because if R1 was too small, it's quite small, a large current would flow onto that plate of C1, or if you prefer a large current would flow onto that plate, depends how you want to think about it. And what you'll end up with is a voltage across C1, because it'll have charged up a bit, through R1. Even though R1 looks like it's connected to the lower voltage, the current is not worried about the voltage. All it would do is obey the directions of the voltage. You can still charge up a capacitor through a resistor. You don't have to have. It is not necessary. If I wanted to charge up a capacitor, I would not need this situation where this is the capacitor and this is the battery. It's just as valid to put the resistor there and the capacitor there. Nothing will really change. Nearly. So there is a negligible change of charge in C1. That's to say, the same thing as C1 doesn't charge up very much. Consequently, if there is no change in charge, there should be no change in voltage. That comes from the well-known time domain expressions for a capacitor, C dV by dt and so on. So we're at half a millisecond now. And so far the diode's done nothing, and the capacitor has passed a small current into a resistor. In the second half cycle, which is this bit here, we have some current flow in the diode. So as the input voltage falls, so this will now be lower, or it will be zero for a short time, half a millisecond, and then this will fall below this value. This will be the more negative end, this will be the more positive end of the source. Consequently, the diode will now be forward biased as soon as, well, it'll be forward biased from the point, from half a second, but it won't conduct, or it won't begin conducting until it's got more than 0.7 volts across it. So it'll be on the point of conduction when it has 0.7 volts across it. So after a very brief period, the voltage has dropped to minus 0.7 volts, this V1, and the diode starts to conduct. And the diode conducting clamps the input voltage. That's to say, it charges up the capacitor. So a large current flows in D1 onto this plate of the capacitor, because this is the more positive end, this is the more negative end. So what we've really done is opened up, we've closed a switch, essentially, between a battery and a capacitor. It's a voltage controlled switch of a kind. Not really, but sort of. We've got the diode in a situation where it's going to conduct, and when it does conduct, it will conduct a very large, potentially, a very large current. And when it does that, it will charge up the capacitor quickly. And that's the key thing. The resistor will charge the capacitor very slowly. The diode can do it very, very fast. And there'll be some charge, and the charge is the integral of the red one, which is current. And having done that, by this point, there will be a voltage across C1 which is not insignificant. That's to say, it makes a big difference as to what's going on in the circuit. And what's really happening is that as we get to the bottom bit here at 0.75 milliseconds, and the diode conduction ceases because the direction of the voltage is, input voltage is changing, and the diode will fall out of conduction. there is already a voltage built in here, not built in, but there is some charge in it which causes there to be a voltage across it. And when the input voltage starts to go up again, it goes up with that voltage as well. So we've sort of added an offset, a DC offset, which is the value of the voltage in the capacitor, on the capacitor, sorry, not in, on, to the input waveform. And that's why it gets shifted up a bit. So you see, this is the top peak for first half cycle, this is the top peak for second half cycle, and because this is steady state thereafter, all of the cycles that follow. And for the conducting diode situation, we've got the lower circuit there. So the key difference is the diode will conduct a large current, or it will conduct enough charge to charge the capacitor quickly. The resistor will not. The resistor is only really there to show you what happens on all the prior further half cycles, because all these little current spikes are the diode conducting very briefly to replenish the capacitor, in just the same way that in the peak detector the diode has to conduct very briefly to replenish the capacitor because it's discharged by the resistor. Same situation here, the capacitor is discharged a little bit by the resistor in each half cycle, and the diode has to conduct very briefly just to top it up. Did I miss anything? Anybody unhappy? Okay. Anybody really unhappy? Have a crack at the problem sheet. There will be another problem sheet. If it is still unclear and there is considerable disquiet, I will go over it again. So, last quarter, we are up to just about here now, just about there. As V1 starts to increase, so from this point here to this point here, V1 is increasing. It's still negative, but it's now going up. And this, the voltage increasing tries to drive a current through the capacitor, C1, and the diode D1 will not support this conduction because it's attempting to reverse bias the diode. So the diode will switch off, the current will cease, so red line drops to 0, and a small discharge current flows from C1 through R, and R is already, as we said, it's very large. So if the diode didn't stop conducting here, the circuit wouldn't do anything of interest, because if the diode was still conducting, I just discharged the capacitor, we're back in the situation when we started. So it's important that the diode stops conducting then, and it's important that R is large, because if R wasn't large, it would perform the same function as the diode, more or less, in the sense that you'd have a large current flowing through R, charging and discharging the capacitor every half cycle. And after a half cycle or two, we'd reach a steady state in which there was no clamping. You just have a high pass filter with a diode that did not a lot. The question of R and C, the time constant of R and C, is critical to making this circuit go. And you could add any additional voltage you wished. So you can have V1, I've got it as V1 is, I don't know, whatever I said it was. What did I have it as? I had it as 4 sine omega t plus 5, where 5 was 0. If I wanted to have 4 sine omega t plus phi, all in brackets, plus 10, that would be fine. So you can add the DC if you wish. It makes no difference to how it works. in a real circuit, C1 has to be able to actually lose a bit of charge through R1. And the reason is, if you've got a signal which has a DC value that you need to restore, but that DC value is not constant, just varies quite slowly, you must be able to follow that changing DC value. So it's the difference between DC and constant. If you can't lose a bit of charge from C through R, once you've got C nice and charged up, you won't be able to discharge it to a lower value to follow that waveform, should you need to. And if I was to turn the diode around, the waveforms will all be reversed, and you clamp the positive half cycle, not the negative half cycle, and that will produce this diagram here. So this is exactly the same operation using exactly the same description, and with respect to time, all the things happen in the same order, except that the diode has been reversed, and the consequences of that are that when previously we said it would be reverse biased, it will now be forward biased, and when previously said it's forward biased, it should be reversed. So we'll end up with the situation where we clamp the positive half cycle instead. So we can put the clamp and the peak detector together. And if we do it like this, we can form a voltage doubler. And the reason is, we will firstly clamp the lower portion, the lowest point of the sine wave. And from that we will gain the difference between that peak and that peak in terms of output voltage. And if we were to then peak detect this, we could say, oh, it will look sort of like that, and then like that, and then like that, and then like that, and so on. So between there, top of the blue one, and the top of the black one, we've gained half the height of the waveform. And that's essentially what this circuit is up to. We have one clamp, that bit there, minus the resistor, followed by peak detector, including resistor. And it is quite literally, you just shove them together. And there is a pretty version. So, yellow is the, what is it? Oh, what is it? Diode. So yellow is the peak detector current, and green is the clamp current. Blue is the input waveform, and red is the output of the clamp, and black is the output of the peak detector. So it's a question of the difference between the black line and the top of the blue line. If I had a question in an exam paper which said, sketch the voltage doubler, you might draw the diagram, and then I might say, for a further few marks, sketch the diagram, sketch a graph which explains its operation. That would be quite sufficient. With less cycles, because it takes quite a long time to draw that, especially if you were drawing in a computer, it takes ages. So if you were to stop sort of there, that would be enough. The important thing is the startup. And you can only get the startup by considering what happens if the circuit's been switched off for a long time. It's not nearly as merit-worthy to say, I'll just assume it's been on for ages and it's in steady state, and I'll just draw this bit here. What happens at the startup is quite important. What did I miss? Oh, I talked about it a bit. Go on then. So, V1 is the input voltage, and when V1 is small, charge flow is low. V1 is low. When V1 is low but positive, so in the very beginning, charge flows through D1 into C1 as described in the clamp, and then when V1 goes higher, no, I'm sorry, that's not right. When, well, that is right, what I just said was wrong. At this point, we have clamp operation, so when V1 is low, I take to mean this bit here, and this bit here, and this bit here, and this bit here, and so on and so forth. We have the same sort of thing you get with the clamp, where we've got the output of the clamp, which is red, stopping at about 0.7 volts below zero. And then when V1 is high, which I've taken to be this bit here, that bit there, that bit there, that bit there, you've got peak detector operation on the output of the clamp, which is red. Now, the peak detector cannot load up the clamp too much. That's to say, if you try and draw too much current out of the clamp capacitor with your peak detector, because the value of R in your peak detector is too small, everything will fall to bits. Because you won't be able to get the clamping operation because the capacitor will empty itself over the course of half a cycle. Similarly, if you load up your peak detector too much, its capacitor will empty itself. So there's a fine balance between what the time constant of the components is and what the signal frequency is. So that's what I've said there. C2 is to be effective. The current R1 should yield a small fall in voltage across C2. So what about the output voltage of the whole circuit? Well, there is an equilibrium. We've got two capacitors, and this capacitor gets charged up when this is small and the current flows into the capacitor through this diode. And then there is a period where there is no energy added to the circuit. This goes away for a bit, it doesn't go away, it's just not. It's not adding any energy to the capacitor. Consequently, all the energy we've got is available in here. And then this peak detector, this diode turns on, and this energy is taken from here and passed into C2. And then it immediately is starting to discharge through R1. So there's a finite amount of energy available for this transfer. It's a sort of charge pumping action. And we can say, well, what will the output voltage be? Well, there's a limited amount of charge available, and it's the charge which is available to be transferred between the capacitors. So we can say, assuming C2 is an effective reservoir, assuming it holds plenty of charge for our application, and is not likely to be discharged within a half cycle, C1 affects the equilibrium output voltage and the time it takes the output to reach this equilibrium. The time it takes is how long your startup time is. If this cycle and this cycle are the same, I think. Yeah, pretty good. Well, that cycle and that cycle are definitely the same. So we've got, what's that, 1, 2, 3, 4, 5 cycles to start up. Good? Nearly. If C1 is small compared to C2, it will only be able to transfer a small fraction of the charge needed to fill C2 on each cycle, and charge will build up in C2 over several input cycles. That's to say, it takes a long time. It's like filling up a large bucket with a cup. You have to do it many, many times. As a result of that, if you are also discharging your bucket while you're filling it up with your cup, it makes a big difference because the amount of charge you can add in is small, but you're always taking it away. So if you choose your capacitors unwisely, you will find the output voltage is extremely sensitive to whatever you put on this circuit, because this circuit must drive something, even if it's just a multimeter, which is high impedance, all very nice. There will be some sensitivity of the circuit to what is loading it, and that sensitivity is determined, at least in part, by the relative value of the two capacitors. And that's what I've said in the third bullet point, essentially. If you had C1 large compared to C2, so this is the other way around, you can put in a large amount of charge per cycle and the circuit is relatively insensitive to what you do on its output. This is filling up a cup with a large bucket of water. You don't have to pour much in. And that's a much more preferable situation than trying to fill a bucket with a cup. So not only can we make a peak detector on the output of a clamp and make a voltage doubler, we can make a ladder of voltage doublers. And you won't often see it drawn like this, but this is a sort of, if you just did a cut paste, not that I cut pasted this or anything, but if you were, then this is broadly what it would look like. So you've got a network of diodes and a network of capacitors and another network of capacitors, and C1, C3 and C5 are the clamp capacitors, and C6 and C4 and C2 are the peak detector capacitors, and R1 is the load. And that is the result of that circuit. So the letters on the right refer to the nodes on the circuit diagram in the prior slide. So we have black line is the input, blue line is the first clamp voltage, which is peak detected to produce the red line. There is a slight drop, but it's very small because the scale of the graph is enormous. And that output of the first peak detector is clamped by the second clamp, which is green. And the output of the second clamp is peak detected by the second peak detector, which is purple. And so on and so forth. So you can generate really big voltages like this if you want to. You can't pull very much current out for the reasons that we already said about the cups and the buckets and the two capacitors. If you're looking in a textbook, and why wouldn't you be, especially if you're looking in an old textbook, usually it's drawn out how it is in this slide, where the capacitors have all been flattened out into a line and the diodes are in between them. It is the same thing, just drawn differently. And you could use this for, okay, we don't have that many cathode ray tubes anymore. But if you wanted, for some reason, I don't know, if you go on YouTube or something, people are now making clocks out of them. So you get a little microprocessor and you have it a little timing crystal and you just have it sat there with the time on it, going round and round and round. They're quite cute, but the trouble is throwing them away now is difficult because oftentimes they've got a fair amount of mercury in them and some other nasty things that actually make the light come out the front. And our friends in Brussels have made it very difficult to destroy them safely. It's never been any more or less safe, it's just a question of how safe you feel. So a lot of people destroyed many CRTs about 3 years ago, and now they're quite difficult to come by. But if you needed an application where you had a high voltage, maybe you wanted to make a spark gap ionizer for something. You need a lot of free electrons in the air, maybe you're doing some experiments using ozone, some sort of particle physics type problem, and you wanted a spark gap, you could in principle make it with one of these. There are other methods which are better, but you could. You can drive a cathode ray tube with it, and if you've got a CD player in your car, or whatever, I don't know. We still have CD players in cars, don't we? My car's about 10 years old, and it's got a CD player. The displays glow in the dark. They are vacuum fluorescent displays, and they need a couple of hundred volts to make them go. And if you wanted to, you could use this Hopcroft-Walton multiplier to make it go. Very briefly, I didn't actually draw out all these diagrams by hand because I'm pretty busy and I'm also pretty lazy. They are all produced from simulating the circuits involved. And the simulation software that I've been using is called LT Spice. And it's really handy for understanding circuits because you can plot any quantity you wish, even temperature if you want to. I won't tell you anything, but you could. It's free to download, and if you go on the course website, there are some circuit simulations for the circuits that are in this course, so you can watch them run sort of in real time. Well, not in real time, in stepped real time. Not only that, I've produced a little script file so that when you click play, you will see what I want you to see. So you don't even have to choose what to look at, it'll be done for you. But you can then bugger about with it afterwards if you want to, and investigate anything you like. So this is for the numerical solution of circuits. That's to say, you have to put in numbers, it can't do equations. Well, under very special circumstances it can. So that's the positive clamp. The other one is the Qt-based symbolic analysis program for electronic circuits, new generation. So obviously they picked a catchy title. This does algebra, so you give it circuits with only linear components, so it doesn't understand diodes or transistors, only does L, R and C, but if you say this is R1, this is R2, this is R3 and so on and so forth, it will give you 1 over J, this, that, the next, R plus whatever, and it will give you all in letters if you want it that way. Also a very useful tool, especially for analysis of 117 problems. Right, I think we're out of time, so there is a review, and another one, and there's that.